My name is Jan Dolze, Product Manager for Patch Clamp Systems at Sutter Instrument. The inspiration for this talk came from questions that I keep getting asked in tech support. A lot of it is, hey, I have this weird signal component. Is it possible the amplifier is broken? And most of the time it's not, because the noise comes from somewhere else. And what I will do is I will take a pragmatic approach. The idea of my talk is in essence to give you a couple means to denoise your own rig. That's why I will not so much focus on the science, the rocket science behind what makes up noise, but mostly on pragmatic approaches. I will very briefly introduce what is noise, then talk about mechanical noise. And here I'll present one case study, microphonics, an anecdote from my own grad student time. And then for the most part, I will talk about electrical noise, and that'll all be current noise in patch clamp recordings. But all the principles I'm going to talk about equally apply to voltage noise in patch clamp and also other modes of electrophysiology. And then I will talk about filtering and the do's and most importantly the don'ts, and then we will have the Q&A session for the entire webinar. There are 5 major strategies to deal with noise. Strategy number 1, first and foremost, is avoid it. Second strategy is avoid it. Third, really avoid it if you fourth possibly can, and only if that is absolutely not possible, then you want to use filters. And I will later tell you why. But first, let's look at what is noise and how do we describe, how do we characterize it. Noise is any unwanted signal component that is superimposed on your signal of interest, your action potential, single channel opening or something like that. It may distort or completely obscure the signal of interest. And one parameter that describes it is the signal to noise ratio. That is the signal amplitude compared to the noise amplitude. Let's take a look at an example. This is a single channel recording. And if we introduce noise, in this case 800 femtoamp standard deviation, then certain components like this flickering at the onset or these close flickers later on in the recording get hard to detect already. And if we increase the noise about 3-fold, it gets completely impossible to even recognize that as a single channel recording reliably anymore. Talking about noise amplitude, there's 2 parameters that people typically look at. One is the peak-to-peak noise and the RMS noise. The RMS noise is the root mean square, and that describes the noise across the entire spectrum under consideration. That is a better measure than the peak-to-peak noise, even though the peak-to-peak noise is more easily recognized usually. A good rule of thumb is the peak-to-peak noise is roughly 6 times the RMS noise. And it can directly be measured in Sutter Patch and the Sutter Patch membrane test. And if I'm not mistaken, HEKA Patchmaster software has the same. When you switch the pulse type from the usual single pulse that it would be to RMS noise, it directly shows the RMS noise. And this is recorded from a deep patch amplifier system with a Ref-E head stage in a 10 kilohertz band. The specification is that it's about 220 femtoamps, so this is even better than specification. I recorded this a couple of days ago on my desk. Let's switch over to mechanical noise. There is no such thing as good vibes in electrophysiology. Vibration is usually transmitted mechanically, either via floor vibration, that happens at a rather low frequency, and can be pretty well isolated through using an air table, a tabletop that floats on air dampers, air cushions, and here's the isolation performance. Lower value means lower transmissibility, so better damping. The frequency range that we're looking at here is between 10 and 70 hertz, so relatively low frequency. You can also have mechanical vibration, mechanical noise by fans or other equipment that touches components. I once had a fan duct sitting on the lamp housing of a microscope that gave me a lot of grief, or microphonics, and also that gave me a lot of grief. And that's an anecdote, a case study that I want to elaborate a little further on. At the beginning of my grad student time, I recorded from taste buds on the red tongue, and I used a recording chamber made of Silgard. That's a polymer that's used in electronics that was glued on a microscope slide in this case. The red tongue was inserted on one end of the chamber. The chamber was filled with saline with a red ringer. And then the amplifier setup looked like this. The recording electrode was actually in the bath for reasons, I forget, there was just the established method in the lab back then, and the electrode that was in touch with the actual taste bud was grounded. And the whole thing sat on a stage that was also grounded. And of course, that causes a capacitance between the conductor here and the grounded stage. And what happened over time is the bottom of the recording chamber detached from the microscope slide. And the way I noticed that was because I suddenly saw myself talking or somebody talking in the hallway or even just walking past in the hallway. I saw that on my electrophysiological signal. And that was because this membrane here created a perfect capacitive microphone. Sound waves would compress the air, and then the capacitance between the bath chamber solution and the grounded stage would cause a capacitive microphone that I would see in my recorded signal. The fix was easy, just cutting out the bottom here, but finding what the problem was took me, I think it was about 2 weeks or something like that. Let's switch over to electrical noise. Electrical noise comes either as intraneous noise, and that could be instrument noise, or there's a number of other noise forms that we don't want to deal with here today because those are not things that we can pragmatically fix in our own setup, but want to refer to the Axon guide that has a lot of detail about what they do and where they play a role. What I do want to talk about is electrode noise and aliasing, an often overlooked form of noise. And then there's extraneous noise, and most predominantly line frequency hum, and briefly also talk about other noise sources. And this is really what's predominant in tech support. Most of the time what people encounter is line frequency hum, and that's also because it's so ubiquitous. So let's talk about instrument noise. The car won't go faster than its top speed. Or for the amplifier, that means the noise you're going to achieve is not going to be lower than what the amplifier gives you, the amplifier noise performance. So looking at the frequency response of an amplifier system, in this case, this is a D-patch. That's the same D-patch that I showed a picture of earlier. And there are two, it has a total of 3 feedback ranges. 2 are shown here. This is the resistive range, in blue the 500 megohm feedback resistor, and this is the capacitive range with the feedback capacitor. And the noise is much lower with the feedback capacitor, and also the bandwidth is much higher, and the Rev-E head stage was specified at over 500 kilohertz bandwidth. The later revisions have a full megahertz. That means that curve would just continue rising all the way to 1 megahertz here. And this was measured open circuit in a grounded enclosure. Why do we do that? Are we trying to cheat to get the best possible noise? No, the simple reason is we want to describe an amplifier property, not the environment. And if we measured it in anything other than a shielded enclosure and open circuit, we would not measure the amplifier performance, but something that we pick up from the outside. And if you don't have a nice box like this, aluminum foil wrapped around the head stage and grounded does a similarly good job. Now, we're going to see a number of these spectra. In this case, it's a power spectral density plot. We're going to see a number of these spectra, and that's why I do want to switch back a little bit to theory. But in the pragmatic approach, I will not go all the way into math, but visually show you how a complex signal, such as our electrophysiological signal, is composed of multiple components at discrete frequencies. So I will show you how you come from a sine wave, that is a signal with a single frequency and a certain amplitude, to a square pulse, which is a complex signal that has multiple frequency components. So what we'll do is we'll compose a complex waveform out of a sine wave, single frequency, single amplitude. We'll add a second one, and a third one, a fourth, a fifth, and so on. Put that in the big blender, and out comes an action potential, or single channel recording, or maybe sodium currents, or as in our example, that square wave. That is a simple example of a complex signal. So what we're going to do is we'll take a sine wave, one frequency, certain amplitude, and superimpose a second sine wave, higher frequency, smaller amplitude. And if we add these two up, we get the blue, the resulting curve here. We do that again, higher frequency, smaller amplitude. We add it up. One more time, higher frequency, smaller amplitude. And it's easy to see how this becomes more and more square. And if we keep going a couple more times, we end up with that square wave. So that is in essence a complex signal that is composed of discrete individual frequencies. And if we do the whole thing in reverse, we end up what's done with a Fourier transformation. That's the same principle, except applied the other way around. We deconvolute a complex signal into its individual components. So this signal postsynaptic events can be deconvoluted into a spectrum. In this case, the Y scaling is different, the magnitude, but the power spectral density would look the same, would have the same shape. The frequency axis in this case is linear. And what we get is we get individual peaks that stick out over the overall contribution here, and this describes what's in this signal. So we'll see a couple curves of this, and I just wanted to make sure that you understand what they mean. Let's go back. This is the same curve that I showed earlier, and the red curve here with the capacitive feedback in the D patch. Let's go back and take a look at what happens if we put a pipette holder on the head stage. And again, this is a question that a customer in tech support recently asked. And well, again, I wanted to investigate the pipette holder, so the pipette holder went in the shielded box as well. And what happens is it doesn't really add that much noise. The Exxon guide says it's about 10%. It looks like it's less than that, but it's across the entire spectrum. With a polycarbonate pipette holder, we also make quartz holders, and this superimposed now in green is virtually identical to the polycarbonate holder. Not too surprising since the whole thing is in air. So the material, the dielectric constant, we'll get to that in a second, does not play that big of a role. So the quartz pipette holder is important for mechanical stability. In terms of noise performance, it doesn't do a whole lot. Let's take a look at electrode noise. The electrode is both a resistor and a capacitor. Let's first look at how the pipette is a capacitor and creates capacitive current noise, and that is proportional to the square of the capacitance. Here is the formula that describes the power spectral density, and here's the capacitance that goes into it in square. And that's the important thing that we need to remember. Capacitance determines the capacitive, the dielectric noise. The resistance also does. That's the electrode voltage noise here. We'll look at that when we look at how the pipette is a resistor. The capacitor, we may remember from high school, two metal discs, conductors, separated by an isolator, in this case air, an air gap. And we probably inserted different materials here to see how that changed. And the symbol in a circuit diagram is this. This is a capacitor. And if we look at our pipette, this is a patch pipette that is filled with intracellular solution and immersed in a bath. That forms a capacitor with a conductor, an isolator, and another conductor. The bath is grounded. The pipette is connected to the input of a head stage, of an amplifier. And of course, the capacitance is not just in this small area of the pipette wall, but distributed evenly across the entire wall of the pipette. And if we remember, the pipette capacitance, which we want to keep low, is proportional to the area, the dielectric constant, and inversely proportional to the distance between the conductors. So how could we reduce the pipette capacitance and along with that the capacitive noise? We could either reduce the wetted area by reducing the pipette fill height, only filling it to the minimum, or by reducing the bath level, or doing both, ideally. Or we could increase the wall thickness by either using thick wall glass or by thickening it, by coating it with Silgard. That's the same material that my recording chamber in an earlier slide was made of. And we could also use quartz capillaries to reduce the dielectric constant, because quartz has a lower dielectric constant than the borosilicate glass that's used for a conventional patch pipettes. The pipette is also a resistor, as I mentioned earlier, and here's the same equation that we had earlier, and the resistance, the electrode resistance here also goes into the noise, the power spectral density of the pipette, and the pipette resistance is governed by the resistance of the tip, the diameter of the opening, and also the length, and geometry plays a little bit of a role. Another form of noise that's often overlooked is aliasing. Aliasing, what is that? It's a form of intraneous noise that happens when you digitize your signal. What happens when you digitize a sine wave like this is the analog digital converter takes a reading at time 0 and 0 plus sampling interval and at equal intervals thereafter. And it only remembers the readings at all these time points and discards the signal in between. And if we do that and connect the dots here, then what we see is a low frequency signal that's not actually present in the original signal. The visual analogon of that is the so-called wagon wheel effect that many of us may remember from the Western movies that were pretty popular a couple of decades ago. Here also we see an artificial, slower movement than what is actually present in this spinning disk. How can I avoid that? By applying the so-called Nyquist theorem, sample with at least twice the highest frequency that's present in the signal, and that's shown here. So again, we sample at t equals 0 and 0 plus sampling interval, and the sampling interval is twice the frequency of the sine wave. And in this case, what happens is we avoid aliasing, but of course, this does not appropriately describe our signal. So what's common to do is oversampling, and 5 to 10 times is a good factor to oversample with. What's shown here is 4 times oversampling. This already gives us a reasonable representation of the signal. How do I ensure that I sample high enough? That's by limiting the bandwidth of my original signal with a low-pass filter, and that's called the anti-aliasing filter. The anti-aliasing filter must be located before the analog digital conversion takes place. There's no way you can remove aliasing from a signal. And all patch clamp amplifiers and most other electrophysiology amplifiers have a built-in low-pass filter that you can use for this purpose. The frequency response is shown here. Again, frequency on the x-axis, amplitude expressed as power square, or power spectral density on the y-axis. And we have the so-called cutoff frequency, or minus 3 dB frequency, from which on the frequency response rolls off. Let's switch to extraneous noise. So far, we've all talked about intraneous noise. That's noise that you can't really avoid because it's inside the system, but you can take steps to minimize it. Extraneous noise can be shielded by a Faraday cage. That's an enclosure made from conductive material. Could be wire mesh here or sheet metal, but then ventilation may become an issue. It needs to be grounded, and at a single point, we'll get to that in a second. Ideally, should be uncoupled, mechanically uncoupled from the air table to avoid introducing vibrations. The table top usually serves as the bottom portion of the Faraday cage. And it can minimize electromagnetic interference, but not shield strong magnetic fields. That's important to understand. And the predominant form of electrical noise, extraneous electrical noise, is line frequency hum, and I labeled it patch clamper's best friend. The reason why is because it'll always be with you. You can't completely get rid of it, but you can minimize it. The most important first step is to recognize I have line frequency hum at all. I sometimes get screenshots from customers showing something like this, and they go like, what is this? My amplifier is broken. And then what I tell them is, okay, this is the membrane test. I tell them, choose a longer pulse duration so you see a couple more cycles of what could be a sine wave-like sinusoid signal, and that is line frequency hum. If it happens at 50 or 60 hertz, depending on where in the world you are, it's line frequency hum. But don't always expect a sinusoidal signal. Sometimes it looks like this. This is a composite of line frequency, the base frequency, with its harmonics. And in a spectrum, it looks like this. This is a really bad case where you have a high peak at the base frequency, 60 hertz in this case. Again, this was taken on my desk here. And then you have harmonics, integer multiples of the base frequency at here 120, 180, 240, 300, etc. hertz, and it goes on. The signal to that looks like in the previous slide. And if you put this head stage into the shielded box, then you get something like this, where this is completely absent and the signal looks more like this. Note that the scaling here is totally different. This is nanoamps. This is about -1 to +1 nanoamps, and this is a couple picoamps. So, how to deal with line frequency hum? Let me reiterate, the most important thing is avoid it. And avoid it by grounding, and you want to use a star topology and avoid ground loops in your grounding scheme. You want to use banana plugs, crimp, or solder connectors, no alligator clips, not for permanent connections, that is. You want to keep all perfusion components inside the Faraday cage. And if that's not possible, interrupt the liquid column with an infusion dripper like this. The downside of the perfusion dripper is it introduces delays in the perfusion. Sometimes there's also a filter in the bottom here that tends to clog up over time. You want to use a dedicated ground point with a star topology. Here's the ground point GP17 that Southern Instrument introduced a couple of years ago. And again, you only want to have one point to the amplifier signal ground. So your ground point in the Faraday cage, all equipment in the cage shall be connected to that. And then there must be a single connection to the amplifier signal ground, usually in the back. And then all components in the rack or on the shelf that the amplifier sits are also grounded to this ground point. And only one path. So here what you would create is a ground loop. Nope. You don't want to have that. You don't want to do that. You may also have to lift the signal ground from the earth ground or the chassis ground. Here shown the back of the D-patch amplifier system. There's this little bracket that lets you connect or disconnect that. You don't, as I mentioned, want to use alligator clips for permanent ground connections. They have small contact points, create an unstable connection that tends to slip off, usually unnoticed, and then you spend a long time troubleshooting because they cause intermittent or high resistance contacts. So don't use this, have a banana instead. How can you troubleshoot persistent noise? You want to run a membrane test or another mode that lets you continuously monitor the signal. If you have, use an oscilloscope. My experience shows that these don't exist anymore in a lot of electrophysiology labs. You want to turn off and unplug everything electrical and watch your signal change. If it changes when you unplug something, then there you have your culprit. You want to touch blank metal surfaces with a grounded wire and again see how the signal changes. When I touch this screw near my objective mount and on the microscope and all of a sudden my line frequency hum goes away, then there you have your culprit. And for this, it's okay to use an alligator clip. Only if you have identified a component, then use a banana or some other more reliable connector. You want to move a grounded sheet of aluminum foil around the head stage to get an idea what direction the noise may come from. And you may have to connect or disconnect the signal ground and earth ground at the back. And also what helps is removing individual ground wires to detect ground loops. In general, you want to not leave ground wires in place that don't give you a benefit. If it doesn't make it better, then there's a pretty good chance that it makes it worse. And with that, what I'll do is I will skip ahead a little bit, skip the second use case scenario with P over N leak subtraction and go to other sources of extraneous noise. Fluorescent light fixtures are pretty popular. Air conditioning equipment, heating and air conditioning equipment, climate chambers oftentimes have switching noise that may even get transmitted through the AC lines. Large scientific instruments like ultracentrifuges, and they also tend to produce large magnetic fields. Elevators are pretty notorious. Cell phones used to be really bad. They've gotten a whole lot better. A subway, a streetcar railway. I recently visited a lab in Israel, and they were concerned because they were building a railway line, a light rail line that was supposed to run right outside the two electrophysiology labs. And that could cause a lot of trouble, and you name it. Let's take a really quick look at filtering. Is it a necessity or is it a last resort? This is a slide that I already showed. You want to limit the bandwidth of your signal to what's relevant for your signal of interest. There's no point recording a slow signal such as Herc currents at an excessive bandwidth like 50 kilohertz or something like that. And you can use the same low-pass filter that serves as your anti-aliasing filter, also keeps your file size small. And if you have to use what's called a hum filter, then you want to use a method that creates a template and subtracts it. That is implemented in the Molecular Devices Digidata 1550, in the Humbug from Quest Scientific that's been around for like ever, and also in software at no additional cost in Sudderpatch software. But my recommendation is don't use it. Notch filters are ineffective and prone to introducing artifacts, so those you definitely don't want to use. You always want to retain the unfiltered signal too. So if you use a hardware item, then record the original signal in addition to the filtered signal. And you still want to minimize the noise in your rig first and not rely on the filter alone. The smaller the line frequency hum is that goes into one of these methods, the better the result. And can only say it again, try to do without. In summary, I talked about mechanical noise, electrical noise, and filtering. And now we're going to switch to the question and answer session and the discussion. And I hope there's going to be a lot of interesting questions here. Thank you very much for your attention.